This is part one of the two-part review for the Earth Science New York State Regents course by Regents Made Simpler. My name is Donnie Rudansky. I will go through this review. Now, on the Earth Science Regent, they give you a reference table, 16 pages, and it's very important to be familiar and know all the different pages because a lot of the questions are based on the reference table. So as I go through the review, I'll go through the different pages of the reference table to help you understand the material. On page 1 of the reference table, you are given these equations. There are 4 equations: eccentricity, the gradient, the rate of change, and density. So first, we'll talk about these 2 equations that are given, the rate of change and the density. So first, you have the rate of change. The rate of change is the change in value over time. So for instance, a question they may ask, they'll give you this data table and they'll say, calculate the rate of change in the inside air temperature from 8 a.m. to 2 p.m. in Celsius degrees per hour. That's the change in value over the time. So in this case, it's from 8 p.m. to 2 p.m. So the change in value is going to be from 24 to 15. So from 24 to 15 is going to be 9. So that's 9 degrees is the change in value. Over the time, it's 2 p.m. to 8 a.m. 2 p.m. minus 8 a.m. The number of hours between that is going to be 6 hours. So the rate of change is the change in value over the time, which in this case is 9 degrees Celsius per over 6 hours. So therefore, 9 divided by 6 is going to be 1.5. That's a rate of change from those 2 points is 1.5 Celsius per hour. That is the rate of change that to know for the Regent. You then also have an equation called density. Now, density, what density is, you have density equals to mass over volume. So first you have volume. Volume is the measure of space, how much there is in a certain space. It's usually measured in cubic meters, which is 3D. And that is volume. Now, inside that volume, you have mass. Now, everything is made up of atoms, which make up into compounds. And that makes up matter. So mass is the matter, basically the number of compounds in a specific space. That's called mass. And that's usually measured in grams for G. So the density is the mass over the volume. This would be low density. That would be high density, right? Low density. And here is high density. You have more atoms, more compounds in a given space. So there's more mass, and that's higher density. Now, an example here, if you have 22 grams of mass and 5 cubic centimeters of volume, it's the mass over the volume is equal to the density. The density tells you how much mass there is per one unit of, let's say, cubic centimeters of volume. So for instance, if this was 22 grams, it would be 22 grams, which would be the mass, over the volume, which is 5 cubic centimeters. So 22 divided by 5 is going to give you 4.4. That's 4.4 grams per cubic centimeter, and that would be the density, the mass per 1 unit of volume would be the answer. Here's another example. You have 7 grams and 3 cubic centimeters. It would be 7 divided by 3, which will give you 2.33 grams per cubic centimeter. Back all the way to the very beginning of the start of our existence, the universe, 14 billion years ago, we have an event called the Big Bang. That is what started it all. The first, you don't have anything. There's nothing. We don't know exactly what this means, but what popped into existence was this very small dot of energy, smaller than the tip of a pin of a needle. And that small energy then expanded and exploded into all directions. And that is called the Big Bang. The Big Bang happened 14 billion years ago. That small dot expanded and exploded into all directions. That energy then cooled down to form the early atoms, the hydrogen atoms. Those were the first atoms. The atoms make up the physical universe. They made up a proton, neutron, and an electron. And those were the first things in the universe, the hydrogen atoms. These hydrogen atoms will then get pulled together by gravity. What gravity is a force is that the universe is basically like a giant fabric. Anything you put on that fabric will cause the universe, the fabric of the universe to bend. So the bigger the thing is, the more mass there is, the more gravity that it will have. The smaller it is, the less gravity it will have. So the more massive and closer objects are equals to the stronger the gravity is going to be. It's like a giant trampoline. If you are very heavy and you stand on a trampoline, it's going to pull the trampoline a lot. Anything around it will be attracted to it very much. That is what gravity is. So gravity is a major force in the universe, and that gravity will help to pull these hydrogen atoms together. The hydrogen atoms come together, and the force of gravity, the more and more, will create this very, very high pressure and high temperature area in the center of this cluster of hydrogen atoms. And that cluster, they will start to collide together by a process called nuclear fusion. Nuclear fusion is the hydrogen atoms inside that there's so much pressure and so much temperature, they will start to collide with each other and releasing a tremendous amount of energy. And that energy will help to form the stars. So stars are formed by nuclear fusion, and that is how stars continue to emit all their light and all their radiation is by the process of nuclear fusion. That is nuclear fusion. Now, these stars will now get pulled together by gravity to make galaxies. So galaxies are these clusters of billions and billions of stars. You have the galaxies are based on their shape. They are identified based on their shape. So you have spiral. It looks like a spiral galaxy. So this is called spiral. This is called irregular because there's no shape. And this is elliptical galaxy because it's shaped like a circle, basically. So it's based on their shape. Now, the different galaxies are all together, and that is called the universe. The universe contains all of the galaxies inside of it. The universe, again, that began around 14 billion years ago. Now, how do we know that the Big Bang occurred 14 billion years ago? There are two proofs that you have to know for how the Big Bang occurred. The first is cosmic background radiation. Is that in the background of the universe, there is a lot of radiation. So if you go, let's say, to Japan and you go to Hiroshima and Nagasaki, you'll see a lot of radiation in the air because an atom bomb was dropped there 60 years ago. So same thing with the universe is that there was a humongous explosion. So there's still some of that radiation in the background of the universe. So that is a proof for the Big Bang. A second is called the Doppler effect. Now the Doppler effect is that if on page 14 of the reference table, you have the electromagnetic spectrum. And based on the different wavelengths, you will see different colors of light. If it's a short wavelength, you see here decreasing wavelength. So the wave is very short. You'll see blue or violet. That's why you see the different colors. If it's a longer wavelength, you'll see it as red or orange. So the Doppler effect is that when scientists look out into other galaxies, they see all these galaxies have this red shift because these galaxies, as you see here, the galaxies are moving away from us. They have this red shift. They must be moving away, causing the wavelength to get longer. So they see them as red. They're therefore inferring that the galaxies must be moving away from us at incredibly high speeds to cause the wavelength to expand a lot, and therefore we now see it as red. If it was going towards us, we would see it as blue, but most of the galaxies have this red shift, so therefore it's inferring that they must be being expanding away. Therefore, the universe must be expanding from a single point, and a proof to the Big Bang by nuclear fusion. So you have the stars are formed because you have, again, the mass of the hydrogen atoms. The more hydrogen atoms you have, the bigger the star will be, the more massive the star will be. And you can see here the star's diagram. You can have an average star or a massive star, again, based on how much hydrogen atoms there are, how much of that gas formed into the nuclear fusion to form these stars. They could grow in size by having more hydrogen atoms, and then they could eventually explode into a supernova or into a nebula, and then they become a white dwarf, which would be the final stages of a star or a neutron star, or become a black hole. That is the life of a star. So you have the characteristics of stars on page 15 of the reference table. So here's the characteristics of stars. So you have many different stars, not all the stars, but some stars in our galaxy. So you have on the left side is luminosity, which is the rate at which a star emits energy relative to the sun. So relative to the sun, how much energy they emit, how bright that star is going to be. The sun is at 1, so therefore the other stars here, the sun is that's where we're located. That's at 1, and the other stars are based on that. So you see Sirius is about 10 times more luminous, 10 times more brighter than the sun. Spica is like almost 10,000 as bright as the sun. The surface temperature is how hot that star is on the surface, so it's relative. So these are relatively low temperature on the surface, and these are much higher. So Spica, they have a higher temperature. Betelgeuse have a lower surface temperature. These are small stars to massive stars, so small is on the bottom, and then these stars are much more massive. They are much bigger than the other stars. On the bottom, you also have the color. So you have Spica is blue. Again, it's high luminosity. It's a big star, and also it is high temperature. These are red. Betelgeuse is a big star, but it's low surface temperature and high in luminosity, and it is a surface temperature of red. Now, you also have the different stages of the stars. First, they start in the main sequence. Here is the early stage, it says. And then again, if the star gets more hydrogen atoms, it can grow in size and become a giant star or a supergiant star. But then, like we saw before, it could explode and become a white dwarf, which is a late stage star. So now the sun is right here, and the sun, that is our star. We are located around the sun. The sun is a main sequence star, and the sun is located in the Milky Way galaxy, like these other stars as well. Again, a galaxy is a collection of billions of stars. So the sun is within the Milky Way galaxy, and the sun makes up our solar system. The sun is referred to as the solar, so it makes up a solar system. And this formed about 4.6 billion years ago. Again, the Big Bang was around 14 billion, and then around 4.6 billion years ago, the solar system formed, the sun formed, and then because of gravity, the other planets will now orbit around the sun. So on page 8 of the reference table, it actually tells you the geologic history. And over here, you can see 4.6 billion is the estimated time of origin of Earth and the solar system. Now, these are called planets. Planets are these celestial bodies that orbit around the stars. So we are on a planet called Earth. And in our solar system, we have 8 of these planets. Now, these planets, they is called the heliocentric model. Helio refers to the sun, and that is called the sun at the center, so heliocentric. That is as opposed to the geocentric model, which was that they used to think that the Earth was at the center, but really the sun is at the center, so it's called heliocentric. And the planets, they orbit around the sun. They don't orbit in a circle. They orbit in an elliptical orbit, which means that it's slightly oval, called an elliptical orbit. And we have 8 planets in our solar system. You have the first 4, Mercury, Venus, Earth, and Mars. These are referred to as terrestrial planets. These are called terrestrial. They are small in mass, they are smaller, and they are higher density, which means that you could stand on them. So these are called terrestrial. The other 4, the outer 4, are called Jovian. These are much bigger planets, Jupiter, Saturn, Uranus, and Neptune. They are much bigger, and they are low density. They are gaseous. You can't actually stand on Jupiter. You would fall through. It is this heavy gas. Now, in between the terrestrial and the Jovian, you have this belt called the asteroid belt. The asteroid belt is a belt of a lot of rocks which orbit around the sun, and that is called the asteroid belt in between Mars and Jupiter. These asteroid belts sometimes collide into planets. For instance, our moon, it collides into it, and it creates these holes called craters. So also the formation of the planets, what you should know is that the gravity caused more dense materials to be pulled towards the center, causing the planets to become layered, that the more denser materials move more to the center, and causing the planets to be layered, which we'll discuss later on in part 2. In the reference table, you have the different data about our solar system. Again, you have the 4 first planets are called Mercury, Venus, Earth, and Mars, which are terrestrial, and the other 4 are called Jovian. So you have the different data about these planets. So first you have the mean distance from the sun. That means how far away they are from our sun, which is the star closest to us. So that's the mean distance from the sun. You can see how Mercury is the closest, and you have Neptune is the furthest away from the sun. You then have the period of revolution, which means how long it takes a planet to make one full circle around the sun. That is called the period of revolution. D is in days and Y is in years. So it takes Mercury 88 days to make one full orbit, one full revolution around the sun. It takes Earth 365 days. That is how many days there are in a year. So that's how long it takes Earth to make one full orbit, one full revolution around the sun. If you do 365 divided by 360 degrees, which are in a circle, that would be 1 degree per day. So the Earth's rate of revolution is going to be, it is moving at 1 degree per day. Now, the period of rotation is how long it takes the planet to make one full spin on its axis. That is called rotation. So revolution is moving around the sun in an orbit. Rotation is how long it takes the planet to spin on its axis. If you see the Earth here, the Earth takes about 24 hours to make one full orbit, one full rotation around its axis. If you did 360 degrees, that's how many degrees there are in a circle, divided by 24, you would get 15 degrees. Therefore, the Earth is rotating at a rate of 15 degrees per hour. So it's 1 degree per day for revolution and 15 degrees per hour for the rate of rotation. Now, the eccentricity of the orbit, again, the planets do not have a circular orbit around the sun. They have an eccentric orbit around the sun. Eccentricity is how ovular the orbit is. 0 would be a circle, and 1 would mean that it's a straight line. So if you see the planets here, they are close to 0. They're not at 0, which would be a complete circle. They are like 0.017, 0.093. Mercury has the greatest eccentricity, which means that it's the most ovular in its orbit around the sun. So the equation for that is on page 1 of the reference table, and you have to know it for the practicals. The eccentricity is equal to the distance between the foci over the length of the major axis. I'm not going to get into it so much now, but it's for the practicals. but this would be 0, and then this would be, let's say, 0.02. Now, the foci are at 2 points that are equidistant to the center of the orbit. So here's the center of the orbit. So the foci is 2 points that are equidistant to the center. The sun is at one of the foci. So here's the sun at one of the foci, and here's another imaginary point that is equidistant with the sun to a point that is in the center of the orbit. So you take the distance between the foci and you divide it over the length of the major axis, which is from the longest points in the orbit, and that would give you the eccentricity of that planet. This would be a longer planet, a longer eccentricity. So the more eccentric the planet's orbit is, the more distance there will be between the planet's foci. Now, also, a planet that is closer, the closer the planet is to the sun, the more gravity that there's going to be, the more gravitational attraction that there's going to be. Like we said before, the closer the planets are, the closer two objects are, the more gravitational pull there'll be. Therefore, the planet will go the fastest at that point. So the planet will move the fastest in its orbit when it's closest to the sun. It'll move slowest when it's away from the sun, the furthest away. So the closer the sun equals the greater the gravity and the faster the orbit, therefore. We have the equatorial diameter, which is how big it is at its diameter. And if you see here, the terrestrial planets, they are much smaller in mass than the Jovian planets. The Jovian planets are much larger in mass. You see they have much bigger equatorial diameter, which means how big it is at its largest point. And you have the mass. These are smaller in mass, the terrestrial planets, compared to the Jovian planets, which are much more massive. You see how they have a much bigger number when compared to the terrestrial planets. However, the terrestrial planets, they are much higher in density. They are high density. They are therefore rocky, higher density. Therefore, you could stand on these planets. You could stand on Earth. You could stand on Mars. But the Jovian planets, you see, they have a much lower density of 1.3, 1.8, which causes them to be this heavy gas. So they're called gas giants, gas planets, the Jovian planets. That is the solar system data on page 15 of the reference table. Now, how do we know that the Earth revolves and rotates? How do we know that they go in an orbit around the sun and that they spin on its axis? There are two proofs for the revolution. The first is that you see different constellations in our night sky. You see different constellations, which means groups of stars. So during the months of June, let's say, you'll see these constellations over here. But since the Earth orbits around the sun, we will see different constellations. So you'll see that in the questions, they'll say, how come we see different constellations in one month, in another constellation in another? It's because the Earth orbits around the sun and moves in a circle, not a circle, a ovular shape around the sun. So we see different constellations. That's one proof. And the second proof is the seasons, which we'll get to soon. And the seasons is that you have winter, you have summer. It's because the Earth orbits around the sun. It doesn't stay in one place. So sometimes the sun's rays will hit directly at different points on Earth based on where it is in its orbit around the sun, which we'll see soon. That is going to be a proof for the revolutions. Now, how do we know that the Earth rotates on its axis? How do we know that planets rotate on their axis? So the answer is that there's two proofs. Is going to be the Foucault pendulum is one proof, and the second proof is called the Coriolis effect. So firstly, you have the Foucault pendulum. The Foucault pendulum is you have a free swinging pendulum that is moving side to side from the ceiling here. So just moving side to side, but it will knock down all the pegs in the circle. The reason is because the Earth is orbiting underneath it, causing the pins to spin, and therefore, even though this is going back and forth, just side to side, it will knock over all the pins in the circle, and therefore that is a proof that the Earth must be rotating, causing these pegs to move and allowing the pendulum to hit all of them over. The second proof is called the Coriolis effect. They have winds on Earth do not move in a straight line. They don't move in a straight line. This is on page 14 of the reference table. The winds do not move straight. In the northern hemisphere, they move clockwise. In the southern hemisphere, they move counterclockwise. That's called the Coriolis effect. If you were on a merry-go-round and you threw a ball to someone on the other side of the merry-go-round, the ball would curve. It wouldn't go in a straight line since the merry-go-round is moving. So we see that the winds curve on Earth. It must mean that the Earth is rotating on its axis. So those are two proofs for rotation. Then we have Earth. So we saw the universe, the galaxies, the stars, the planets. And then we have our planet, which we are on. That is the planet called Earth. Now, Earth is the only planet we know of that can sustain life. That has life. So there's different characteristics of Earth. So here on page 1, you have the average chemical composition of Earth's crust, hydrosphere, and troposphere. Again, everything in the universe is made up of atoms, of elements, and these elements come together to make up different compounds. So you have different parts of Earth. You have the crust. That is the top solid layer of the Earth. That's what we're standing on, the crust, the land. But also you have the the oceanic crust. You have the continental crust, which we got to. But that you'll see its percent by mass is mostly made up of oxygen and silicon. But the percent by volume, it's mostly made up of oxygen, as you see in this chart here. The crust. The hydrosphere, that refers to the oceans, which are 70% of Earth's surface. You have to know that 70% of Earth's surface is covered in water, covered in the hydrosphere. That is made up of 66% hydrogen and 33% oxygen. That is H2O. So it's made up of water. That is hydrosphere. The troposphere, that is the layer of gas that surrounds the Earth, called the atmosphere. The troposphere is the first layer of the atmosphere, and that is made up of mostly nitrogen, which makes up 78%, and oxygen, which makes out about 21% of the atmosphere. That is what we, the air that we're walking in, that we're breathing in. Now we have the seasons. Now, what causes the seasons on Earth? We experience different seasons. You have the winter, the summer, the fall, and the spring. So what causes that is that the Earth, the sun's rays will cause, the sun's direct rays will cause the different seasons. Now, the Earth is not straight like this. The Earth is actually tilted at an angle of 23.5 degrees on a line, as you see here, on a line that is perpendicular to the plane of the Earth's orbit. So this is a line that is the plane of the Earth's orbit as it orbits around the sun. And this line right here is perpendicular. It makes a 90-degree angle with that plane of the Earth's orbit. And you see how this is the axial tilt. See how it's tilted back 23.5 degrees to a line that is perpendicular to the plane of Earth's orbit. Now, this tilt will cause different seasons. And sometimes it'll be hot in the southern hemisphere, and sometimes it'll be hot in the northern hemisphere. There are two main reasons why a place is hot or cold on Earth. One reason is the angle of insolation, which means how direct the sun's rays are. So, for instance, how direct the sun's rays are. And insolation means incoming solar radiation, which means radiation from the sun. So there's two main ways for a place to be hot or cold. The first way is the angle of insolation. If a place gets direct sun rays from the sun at 90-degree angle, that is the most intense angle to get at 90 degrees. That is going to be the hottest place on Earth. If it's going to be, let's say, a less angle, like 40 degrees, or 15 degrees, it won't be as hot. It will be much colder. That is called the angle of insolation. If you have direct sun rays, it's going to be the hottest than compared to a place, let's say, in the North or South Pole, which will get less direct sun rays. The second way is the duration of insolation, which means duration, how many hours of daylight that place gets. So since the Earth is tilted, if you see here, for instance, in the southern hemisphere, they're getting more duration of insolation. So we'll see, since the Earth stays tilted as it orbits around the sun, you will have the different seasons. So first you have 4 seasons, and you have 12 months. So every 3 months is a new season. So first we'll start off with the winter solstice, and ironically, that is when the Earth is closest to the sun, actually, during the winter solstice. And we're really talking about the northern hemisphere, what they are experiencing in the northern hemisphere. So in the northern hemisphere, we have the winter solstice on about December 21st, and that is the first day of winter. And what happens is the sun's rays hit directly at the 23.5 degree south line, which is the Tropic of Capricorn. And since it hits directly at this point here, then the southern hemisphere will be facing towards the sun and will be hotter. But the northern hemisphere, where New York is located, we're located in New York, which is in the US in the northern hemisphere, it is tilted away from the sun, so it's going to be colder. Since we're tilted away, we get less direct rays from the sun. In the southern hemisphere, they get more direct rays, so it's going to be hotter, but it's going to be colder for us in the northern hemisphere. So for someone in New York, the sun will appear much lower in their daytime sky. See here on December 21st. On December 21st, the sun will appear much lower in our daytime sky because we're tilted away from the sun. Now, also, we have less duration of insolation. We get less hours of sunlight. You can see the North Pole is completely in darkness, but in the Southern Hemisphere, they get more hours of sunlight. For us in the Northern Hemisphere, we get less hours of sunlight. So for those two reasons, less direct rays and less duration of insolation, it's going to be colder in the Northern Hemisphere. Therefore, it's referred to as the winter solstice. Now, again, 3 months later, After December 21st, you then have March 21st, and you have the first day of spring. This is called the spring equinox, and the sun's rays hit directly at the equator, And it's called the equinox because it's equal, that all places on Earth will have 12 hours of sunlight and 12 hours of darkness. It's going to be warmer during the spring equinox than it was by the winter equinox for us in New York. And that is because we get more direct sun rays. You see how it's hitting at the equator. So we're facing a little bit more towards the sun and getting us to be warmer. Now, during this time, the sun will rise in the due east and then set due west for us in New York. And you see how it rises further up in the daytime sky. It rises up further in the daytime sky. And that is by the spring equinox. Now, 3 months after the spring equinox, 3 months after March 21st, is going to be June 21st. And that is the first day of summer. That is called the summer solstice. And during the summer solstice, the first day of summer, you see how the 23.5-degree north line, the Tropic of Cancer, is now facing towards the sun, getting the most direct sun rays. Therefore, the northern hemisphere is facing towards the sun. Therefore, it's going to be hotter for us in the northern hemisphere. It'll be colder for those in the southern hemisphere, but it's going to be hotter for us in the northern hemisphere because we get more direct sun rays. And we have more duration of insolation. You can see how more of the sunlight, we're getting more hours of sunlight during that time because we're facing towards the sun. That's called the summer solstice. And since we're facing towards the sun will rise much higher in our daytime sky, will rise north of due east and set north of due west. It's gonna go much higher in our daytime sky during the summer solstice. Now, 3 months after that, you have the September 21st. And on September 21st, you have another equinox that's called the fall equinox. And that is when the sun's rays will hit directly at the equator as well. Again, by the equinoxes, the sun's rays hit directly at the equator. And when it hits it at the equator, it's called the equinox because we have 12 hours of sunlight and 12 hours of darkness. So you see, for someone in New York, you see how the sun rises due east and sets due west during that time. That is by the fall equinox. So again, you have the 4 seasons. The winter solstice, we're facing away from the sun. Therefore, it's going to be less direct rays and less hours of sunlight. So it's going to be colder. And then you have 3 months later, the March 21st, the first day of spring, hits directly at the equator. Then you have the summer solstice. It hits directly at the 23.5-degree north line. So it's going to be hotter for us in the northern hemisphere. And then you have the autumn equinox 3 months after that, September 21st, where it hits again at the equator directly, causing the equator to be the hottest and having 12 hours of daylight and 12 hours of darkness for all places on Earth. So those are the 4 seasons and a proof for the Earth revolving around the sun. Hi, I'm Donnie Rudansky from Regents Made Simpler, and you can purchase this entire course for only $89. This includes a 2-part review of all the material you have to know in a simplified version, plus video review with visuals of the past 2 Regent exams. I am putting up one for the 3rd as well, for June 2023 as well. So you can get that all for $89, which is actually less than a typical 1 session with a tutor, a personal tutor, which usually you will need a few sessions of, but you can watch this course at your own pace for only $89 and know everything you need to know for the upcoming exam in just 3 hours without using any flashcards or anything like that, using this course. So that's on the bottom right here. Clicking there, go to regentsmadesimpler.com. You can see this course here. I could show you a little bit of it. So here we have biology and earth science as well. And what you'll get, again, is a 2-part review course going over all the material you have to know in a simplified version. And as you see, plus video review of visuals of the past Regent exams. So here you can see here, it's not just a video of me explaining the material. It's also me with visuals from the reviews going over the questions as well, and going over why the answers were wrong as well. So be sure to check that out here on the bottom, clicking here to go to regentsmadesimpler.com.